Hello, good day everybody. Can you hear me? Can you see my screen?
Yes, sir.
All right, thank you for the response. Let's take a moment to scan your attendance and then we'll begin our class today. All right, let's begin our class today. Good day everybody. Welcome back to our class again. Yet it is yet another new week again. Right. So throughout the past week, we've been covering topic 5, and then in today's class, I realized that next week is your holiday, right? So what I'm trying to do today is continue from where we left off last class, and we are going to finish chapter 5 today. Chapter 5 is a relatively short chapter, and it's a relatively simple one as well. So I really do hope that I promise that today's class is not going to be long. We'll finish really quickly, but I'll need your brief attention throughout this short moment because you're going to need this for your assignment today. All right, so let's get back from where we left off. So chapter 5 talks about basic combinational logic. Let's just run through a quick review on what we did last class. So we talk about combinational logic, which consists of 2 or more logic gates, and we talk about that this kind of logic, combinatorial logic, has got no memory. Okay, it does not remember what you give as the input in the past. Okay, it only knows what is the input for the present time. We'll talk about memory in the upcoming classes, right? So for now, just know that for combinatorial logic or combinational logic, you do not have any kind of memory. All right, so we also talk about these are the few types of basic combinational logic. These are the 4 types of circuits. We have AND OR invert, or AND invert. So as you can tell right now, like so they are this 2 above, like they are dealing with SOP, and this 2 below, they're dealing with the POS, products of sums. Okay, right. So this is the example of AND OR. We went through this. And then AND OR invert. So AND OR invert actually makes it possible for you to implement everything using NAND gates, right? Or AND invert, the same thing. And we also talk briefly about the levels of logic. So what's the levels of logic is the largest number of gates a signal must pass through from the input to the output. Okay, for example, over here we have the level of logic to be 1 gate, 2 gates, 3 gates. So for this combinational circuit over here, we have level of logics equals to 3 because this is the highest number of gates that a signal needs to pass through. Okay. Right, so and we also talk about the important point last class, which is the universal property for NAND gates and NOR gates. So what we talked about was we realized that using NAND gates and using NOR gates, we can pretty much construct any other gates. So that includes NOT gate, OR gate, AND gate. You can even construct another gate. Okay, using NOR gate, you can construct NAND, and using NAND, you can also construct a NOR. Okay, so that is why there's 2 gates, universal gates, NAND gate and NOR gate. They are very special because they can be used for any kind of logic circuit. Okay, all right. So we also did cover on the conversion of a normal network. So for example, what we did over here was this was implemented using AND gate plus OR gate, right? We also did the conversion, how you can convert something which uses AND gate and OR gate into using fully NAND gate. Okay, so we did cover on using graphical conversion, which means to say you convert using the schematics by drawing bubbles. Remember, we did that, and we also did using De Morgan's theorem. So you can also do double inversion, put the double bar on top, and then you find that you can use De Morgan's theorem and simplify that, and you get a NAND circuit. So what we did focus on was a conversion by diagram. So we did for NAND and we also did for NOR. And I hope that during the your quizzes also last week, you'll manage to apply what you learned in the class. All right, so that was what we did in short last class. Okay, so today we will continue from where we left off. We will talk briefly about factoring, and factoring is not something new to you guys. I believe you guys did factoring already. It's just something you need to know just for the sake of the term, okay? So make sure you are familiar with this term factoring because you might encounter this in your questions or in your assignments or in stuff like that. So factoring is a technique to use to reduce the number of literal. So for example, if you have like an expression over here, so we can factor out common terms. Okay. So for example, what we did over here is we factor out the common term, which is a over here. Right. So if you factor that out, what we find is that we can reduce the number of gates. Okay, for example, over here we have like an expression requires 4 gates and 9 gates inputs. Okay, it requires a lot, but factoring can help you to reduce that number. Okay, so that is all about factoring. I don't think we need to do any exercises. You've been doing factoring all this while, right? Just the term over here. Okay, so this brings me to next to the key lesson for today. The key item that I want to cover today is something called propagation delay. Okay, so I need your attention for the next few minutes, and then we'll end our class today after this. All right, so let's talk about propagation delay. So first, let's take a look at this circuit over here. This is a simple NOT gate. Okay, in a simple NOT gate, so okay, let me just if you give an input to this simple NOT gate, if you give a input value of 0 and then you get 1, right? That is what we know from a simple NOT gate. So I'm now going to draw the timing diagram for this simple NOT gate. This timing diagram is going to look like this. So this is the input, and okay, maybe this is the output. So input you have 0 and 1, output you also have 0 and 1. Okay, this is the time. Okay, time. Okay, so what happens over here if I start to give a value of something to the input? Okay, so let's say the input from the beginning of time is 0, and then after some time I decided to flip the switch and then change this input to 1. Okay, and then this input stays 1 over there. Okay, so if I were to ask you to draw a timing diagram, what the output would look like. So you would maybe draw a timing diagram which looks like following. So the output is just the inverse of the input, right? So the output would be like that. And then I will draw it like this, right? No problem. Okay, this is considering there is no delay in the NOT gate. Okay, this is like the perfect situation where the moment you flip that switch to 1, and then the output changes instantaneously. Okay, this is like the perfect NOT gate. But as we all know, in this world, there's nothing that's perfect. Not even logic gates, not even this NOT gate. Okay, so what happens when we flip this switch to 1 is that this NOT gate will require a little bit of time to process that, and then you would see the change. So this is what happens instead. Instead of this having this green line, changes instantly goes down like that. This NOT gate actually requires a little bit of time to react to that changes. Okay, so in the real world, what really happens is that the signal is like high over here because the input is low. It doesn't react instantly like that, like over here. In the real world, it will take some time and then it will react. Okay, get what I'm trying to say over here? So it will take a little bit of time to process that input change, and then it will react to that changes. Okay, so this is what you are seeing over here on this left side. So this time that it takes, right? this time over here, the time between the moment you flip that switch and then and after that the reaction of that NOT gate, this is known as the propagation delay. Okay, propagation delay. All right. So thankfully, this time is not like a very big value. It's not like 1 second or 2 seconds. It's like 1 nanosecond. Okay. Typically, it's like 1 nanosecond or 2 nanosecond in that range. Okay. So maybe like I would just write here 1 nanoseconds or something like that. Okay. So different manufacturers, maybe different kind of gates, they have different kinds of delay, different values of propagation delay. But in all of these cases, this delay, they are actually too quick for anybody to notice at all. If you were to just use your eye and see, you would see like there's no difference because 1 nanoseconds, nobody can tell the difference. Okay, but if you were to put this into an oscilloscope, this is what you will see. Okay, propagation delay. Just bear that in mind, because in this chapter we are going to see that in the real world we do have this propagation delay happening, and this propagation delay can cause problems. So what's the problem? Okay, so the problem is known as statics. Okay, or hazards. Sorry, the problem is known as hazard. Okay, hazards, or sometimes we call them glitches. Okay, so remember the time when you have somebody might tell you, oh, I have this glitch in my computer program. I have this, something that's wrong with my computer program. Suddenly the program just crashed. I have this glitch. So this glitch is what they are talking about. So glitch means that the program did not run the way it's meant to be run. Okay, so in other words, glitches means there's some kind of error. Okay, error. So same thing, hazards means there's some kind of error in the output, and it is usually caused by propagation delay. All right, so this errors at the output, yeah, hazards means it's an error of the output is caused by propagation delay. So one example of this hazards is that the output changes. So output changes when in fact it's not supposed to change. Okay, so let's say you have the output who's supposed to stay 1. This is the correct case. Output value is supposed to stay at 1, but in a real scenario, when you test it out, the output doesn't stay at 1, but it goes down and then it goes to other values. Okay, so this is the glitch that we talk about. Glitch, or also called hazards. Okay, in digital logic, we call them hazards. So I'll use this term hazards from now on. So these hazards are usually caused by propagation delay. Okay, so there are 2 types of hazards. One is known as static hazard. The other one is known as dynamic hazard. So what's the difference? Let's just take a look at static hazard. So the static hazard is when the output change only once. Okay, so let's say you have the output that's supposed to stay at 1, but then this output misbehaves a little bit. It changed like that. It changed 1 time to 0, and then it's back to 1. Okay, it changes only one changes. Okay, for a dynamic hazard, you can have multiple times. The changes can be like that multiple times. Okay, so you can have 2 types of static hazard. This is they are called static 1 and static 0 hazard. Okay, so you have 2 types of hazards: static hazards, dynamic hazards. All right, and in static hazard, you have static 1 or static 0. So it's very simple. This is what static 1 hazard look like. Okay, when it's supposed to stay at 1, but for a brief moment, maybe for 1 nanosecond, it dropped to 0, and then it's back to 1. Okay, your eyes will not even be able to notice that change. But if you're running some kind of a machine or computer, this computer will be able to notice this momentary change, and that's not supposed to happen. Okay, this can cause problems down the line. Okay, let's get back here. This is known as static 1 hazard. Right. So static 0 hazard is the other way around. Okay. So static 1 hazard is primarily happens with a SOP expression, okay, sum of products, and you would usually find it in this NOR circuits. The static zero hazard is the other way around. So the static zero hazard looks like this. So the original output like should be 0 all the time. But if you have static 1 hazard, this value does not stay at 0, but for a brief moment in time, this value just spikes up to 1 like that, and then it continues go at 0. Okay, it spikes up for this brief moment, and then it goes back to 0. Okay, so this is known as a static zero hazard. The static zero hazard primarily happens with POS expression. Okay, post expression. Okay, so we've covered static hazards. We have static 1 and static 0. So what about dynamic? So for dynamic hazard is a combination of both. You can say that. Okay, so this is what a dynamic hazard looks like. So the change in output occurs more than once. So for example, over here, from 0, it changed to 1 for a brief moment of time, and then it changed back to 0 for a brief moment of time, and then it goes back to 1. Okay, same thing over here. It changes, and then changes again, and then it goes back over here. Okay, so bear in mind that these changes, they are not in the truth table. Okay, they are not in the truth table, and they are not supposed to happen. But in real life, it happened because of propagation delay. So remember, in truth table, we did not ever consider what if there is any delay in the logic gates. But in reality, there is. So in an example after this, I'm going to show you how exactly can this happen, and I really hope that you can figure this out also. Okay, let's suppose we have this not so beautiful circuit over here. I couldn't find a proper circuit. I just draw it like on this slide yesterday. Okay, so imagine this to be a very beautiful and nice looking circuit, right? Okay, so first, this circuit, let's get the output expression over here. For this circuit, I'm trying to illustrate to you how can a hazard happen. Okay, so let's try to get the output over here. F is OR gate, so we have a plus somewhere here, plus with that is AB, A and B, and then we have B, bar, and C. Okay, so let's just keep this expression over here for our reference. Okay, so let me show you what can happen with this. So let's suppose you have here the value of A to be 1. Let's just take this example, okay? So if everything is 1, then let's try to compute what is the output, okay? The output would be, so let's try to do this, 1 and 1. So over here we have a 1. And then this goes to here. And over here we have 1. We got here 0, 0. And over here 0 and 1, you get a 0. And over here you get 1, or with 0, you would get 1. Okay, very simple. Okay, now I'm going to do something that will allow you to see when hazards can happen. Okay, say now I decide that I want to change this value of B. Okay, from this value of B, I want to change it to 0. Okay, so what happens? So let's say all of these gates has got a delay. Okay, this gate has got delay, this gate has got delay, and let's, okay, the delay can be very small, 1 nanoseconds, but this delay will add up if you put it stacked with one another like this. Okay, but let's see what happens if I change this value. So the moment I change this 1 into 0, what happens? So after 1 nanoseconds, this output becomes a 0. Okay, so this one here becomes a 0, 0 and 1. This one changes to 0. Okay, cool. And at that moment of time, this one here, because this is 0 and this is 0, this one here becomes a 0 also. Okay, but what happens like down here? Because in this branch, right? Take a look at in this branch, this change does not instantly go to this gate. It's got to go through this NOT gate over here first. Okay, so because it has to go through this additional NOT gate, so this changes in this changes here becomes a 1, and then after some time, only then this one becomes a 1. And after that, what happens is that 0 and 1, and then let this one goes back to 1. Okay, so I hope you're beginning to see what I'm trying to say over here. You change one thing over here, and at that small instant of time, this F output over here changes to 0, and then the moment the signal also reaches this, and because there's 2 gates over here, and then the moment this signal reaches this NOT gate and then propagates to this, and then this output at its F goes back to 1. Okay, so what happens at the output was the function F is supposed to be 1 all the time, but what happens was that because of propagation delay, the F momentarily goes down like this and then goes up like that. Okay, so 0, so this is 1 and this is 0. Okay, so this is what we call a hazard, and in this case, this is a static 1 hazard. Okay, static 1 hazard. So you can imagine that if you have another gate over here and then some other gates running, then this delay will become more and more obvious. Okay, so what I want you to see over here is that one thing is that when you change this, the signal that goes through this path and the signal that goes to this path, they arrive at a slightly different timing. Okay, because why? If you go, the signal that goes through the top path over here only has to go through 1 gate and 2 gates. But the same signal goes through this path, 1 gate, it goes to 1 gate, 2 gates, 3 gates. So it arrives at the OR gate at a different time because of propagation delay. Okay, and so because of that, we see this dip in the output, just a momentary dip in the output, and this is what we call hazard. Okay, is that clear, everybody? So this is how hazards can happen in this circuit. Anyone has got any question? Let me take a drink.
Sir,
Yeah.
the delay can happen to all 3 inputs, or is it like it sometimes happens to this input and then it changes to a different input? How does it work exactly?
The delay. Oh, you mean like let's say I change this one. Does the hazard happen? Is that what you mean?
Yeah.
Okay. So the thing is, if you change this, do you think there will be a hazard that's going on? Okay. The reason this hazard happens when I change B, the reason I chose this B is why? Is because I know that this signal over here, B, goes through 2 paths. And these 2 paths arrives at the output at 2 different times. Okay. The first path over here arrives at the output after like going through 2 gates. The second path over here arrives at the output after going through 3 gates. So because of this difference in arrival time, the signal arrival time, there could be a potential hazard. It doesn't happen every time, but there could be a possibility. Okay, but what if I change the value of the other one, right? What if I change the value of the top one? Okay, if I change this 1, if I change to 0, I see that it doesn't affect any other path, it seems. Okay, so there is, for a simple circuit like this, of course we can say, okay, there is no possibility of a hazard happening, but for a large circuit there might be. Okay, but I know what you're concerned about. So how do you know which input should I change over here that can allow this hazard to happen, right? That is what I am going to tell you next. So let's say you have this circuit like this. So how do I know that this circuit has got this hazard happening? And how do I know which input leads to the this hazard happening. Okay, that is what I am going to show you right now. So let's go back to this expression over here that we wrote earlier, right? So let's say right now, okay, just imagine right now, you have this circuit and you have this expression, and then like you are working this out for a client, okay, like for some company. So let's say this is like a super complicated system. Okay, let's imagine this, even though right now we are working with a simple one, but you can imagine this becoming complicated. So you know that this system has, this is the Boolean expression for the system. And now your client wants to know whether this system that you come out with has got glitches, has got hazards. How do you know how to analyze this circuit, whether or not you have any kind of glitches or hazards in the circuit? Okay, I'm going to show you here. Right now, it's going to be very, very simple. Okay, so pay attention. So let's look at this expression over here. What I'm going to do now is to draw the K-map for this expression. So I'm going to draw this K-map for this expression, 0, 1. Okay, this K-map here. K-map. Okay, so previously from the K-map you get expression, right? Now let's do the reverse. From the expression you put into the K-map. So what we can do is like this. This is A and B. This is 1 and 1. So for the boxes that are both ones, you can mark that as 1. So A and B are both 1. So A1 is along this row, and we have here 1 over here and 1 over here. Okay, A, B. Okay, right. And for this one is 0 and 1. So 0 and 1 for B and C. This is B and C, 0 and 1. So which is here. Okay, so you can imagine that this is the map that you have. And how do you get this? How do you get this? Is by grouping these two together. Okay, if you group those two together, then you would get the above map, the above expression. Group this. This one would give you B bar C, and if you group this one would give you A B. Okay, so that's how we get this expression over here, A B bar C. So how do I know at which point the hazards happen? Okay, this is the important part. The hazards can happen when you have two adjacent ones that are not in the same group. What do I mean by that? Okay, let's take a look closer in this map. So we want to have two ones that are adjacent to one another, which means side by side or top and bottom, but at the same time, they're not in the same group. Okay, so let's take a look at these two ones. Are they side by side? Are they top and bottom? Yes, they are adjacent to one another. Are they in the same group? Yeah, they're in this same one red, in this red circle. So they're in the same group. So no issues with this. If they're in the same group, there's not going to be any hazard. Let's take a look at these two ones. So these two ones are also adjacent, but are they in the same group? Yes, they're also in this, within this red circle here. But take a look over here. These two ones, they are side by side, which means they are adjacent, but are they in the same group? No, they are not in the same group. Okay, this one belongs to this group on the left. This one over here belongs to this group on the right. So this is how we spot that this is where the hazard can happen. Okay, within these two ones. Okay, that is in this box and in this box. Okay, so I'm just going to draw this group over here, the group in green. Okay, so in this spot, what is the value of A, B, and C? In this spot, the spot that I marked here, X over here. The value of A, B, and C over here is 1, 0, 1, correct? If I stand in this box, what is my value of A is 1, my value of B and C is 0, 1. So ABC is, I'm writing here 1, 0, 1. But if I stand here in the other, if I stand in this box over here, what's my value of A, B, and C? My value of A is 1, my value of B is 1, 1. Okay, so what happens over here is that the glitch, we can see over here, the glitch happens when we transition between these two values, okay, from 111 to 101, or from 101 to 111. Okay, so that was what we did just now, right? Remember, we set all this value to 1, 1, 1, and then what happens was I changed this one to 0. So that is how I know, oh, I changed this value over here and I get a glitch. It is from this K-map. Okay, is that clear, everybody? Any question for this? How to spot which part you have a hazard?
Yes, sir.
Okay, okay. There's no question. Now we already spot this hazard over here. Now the next question is, how do I fix this? Okay, so how do I fix this? So the way you fix this is already on the screen. So the way you fix this is you put a redundant group over here. Okay, you put a redundant group over here that that encapsulates this too. So this redundant group over here will give you an additional expression over here. So in this case, it is A, C. Okay, so this AC. Yeah, it's AC. So your expression of F that does not have any kind of hazard looks like this. So it's got one extra term, AB plus B or C plus AC. Okay, this is the function with no hazards. No hazards. So if you go ahead and draw this out, you would find that it looks pretty much the same like the old circuit AB, and you still have this B bar, then you have C, and then you also have this AC. Okay. Let me draw this out here. Here. A over here like this, and you also have C here like this. Okay, and they can all go through an OR gate. That. Okay, so okay, you guys can draw this much more beautiful than my drawing over here. Okay, so what is the difference between this green circuit and then this red circuit? So what you will notice is that no matter what path you take, you would see that you would arrive at the output at the same with the same number of gates. Okay, so you would go 1, 2, 3. So you go 1, 2. Then you will also go. If you were to do the same experiment like what we did just now, you would find that all the values they are changed in time without causing the delay, without causing the glitch at the output. So that is how you solve this circuit with glitches by adding some redundant term above here. Okay. Right, so let's go through a few more examples so that you can see this clearly. So this is showing over here a circuit, and then this one has got this 4 gates over here. From these 4 gates also you can see that some signals go through more gates than some other signals. Okay, so in this one we will draw this timing diagram. We will draw this timing diagram of the following combinational logic circuit. The NOT gate has got a 0.5 nanoseconds delay, and the other gate has got 1 nanosecond delay. Okay, so this one is 0.5 nanoseconds. All the other gates has got 1 nanoseconds. So let's draw out the timing diagram to see and visualize the static hazard. Okay, so this is what I have in my timing diagram. So this was the circuit from just now. And let's break this circuit down to S bar over here. And this one, let's just name it K0 and then K1, okay? Just to be consistent with what I have here on my timing diagram. So let's see how we draw the timing diagram for S bar first. So S and S bar, they are just inverted version, okay? Right, so let's start to draw S bar over here. So we see that S bar, let me change my color, ink color, okay. So we see that the S bar is just the inverted version, right? So over here is 1 that we are going to draw here, 0, 0, 0. And then we go to 1, then 0, 0, 0, like that. Is it that simple? No, it's not that simple. Okay, in this case, what I've shown you is I'm drawing S bar without considering the propagation delay. Okay, I'm not considering the delay. So this 1 over here instantly reflects as 0 over here. Okay, right. So that's not the case. Unfortunately, that's not the case. This 1 over here does not instantly reflect to a 0 over here. It's got to take some time. Okay, how much time? For this gate is 4.5 nanoseconds, right? That was given to you in the question. So what that means is that instead of starting from the beginning over here, my NOT gate only reacts to that change to input after about 0.5 nanosecond. So that means that my waveform is not going to start from here, but it's going to start after 0.5 nanoseconds. Okay, it's going to start halfway. It's going to start at this point. Okay, so one stretch over here like that is going to be one stretch over here. Okay, so and then one stretch over here is going to take one stretch over here. One stretch over here is going to take here. Okay, and then like now this changes to 0. So that changes to 0. It does not react instantly at this point. Okay, so after 0.5 nanoseconds, which is this portion over here, then it reacts. Okay, and then like this portion over here reacts to this one, and then now it changes back to 1. Okay, then it does not change instantly over here, but it takes 0.5 nanoseconds, and then it reacts to that change. Okay, over here it's just one portion. Here is just one portion. Okay, so we can see that this waveform is actually just shifted. Okay, shifted by how much? By 0.5 nanoseconds. Okay, so for the first 0.5 nanoseconds over here, we do not have any value. Okay. Okay, so the signal is not defined over here. For this is 0.5 nanoseconds. Okay. Okay, why is it not defined? Because of propagation delay. That is for the NOT gate. Okay, so let's take a look at this one. We've got S bar already drawn. Now we want this K0. K0. Let's draw K0. So K0 depends on I0 and S bar. So S bar is over here and I0 is over here. So I0 is very simple value. It's 1 all the time. 1 all the time. Okay, so which means it is 1 all the time, which means this output will just depend on what this value of S bar is. Okay, so for the first 0.5 nanoseconds, so we are looking at these two signals. Okay, so don't get confused. Let me change my ink color again so that it's visible. Green. So we have over here I0 and S bar. So these two signals, we are going to AND them. Okay, so for the first 0.5 nanoseconds, we do not have any signal over here. So even though you have signal over here, right? For this part, right? You have something over here, but there is no defined signal over here. Okay, there is nothing over here. So the output at K0 cannot be anything meaningful. So it's also like undefined over here. So undefined means in digital logic, when you say undefined, it means that the signal is like flipping. It can be 1, it can be 0, it can be like flipping to from one state to the other. Okay, so it's not defined for the first 0.5. So it is only after that we have some signal for S, and then we can perform the operation over here. So let's see over here, we have 0, we have 1, so which means AND 0 and 1 together, then you get a 0. Okay, you might be tempted to draw it like that, right? So 0 here, 1 here, and the changes is instant. You just draw this 0 here. But that is without considering there is propagation delay. Okay, so we know that for this gate also there is a 1 nanoseconds delay. So which means that you do not start drawing from here, because if you draw from here, it means that your gate is instantly reacting to the changes in the signal. So your gate, your AND gate only starts to react after 1 nanosecond, which is at this point. So this part over here, ended together with here, you get 0. So this is where you start. This is where the result appears after 1 nanosecond. So this block over here is 1 nanoseconds. Okay, this is 1 nanosecond. So it takes 1 nanosecond to react to process the signal. Okay, to process the signal, and then it appears over here. So now let's process the next segment. So we have 0 here, then we have 1 over here. So it means that the result appears at here. We have 0 again here, and we have 0 up here. Okay, it's going to be here again. So we have half a segment here, 0. So we have half a segment here, 0. And then it changes to 1 over here. Now it also changes to 1 over here. Okay, so the top portion is just 1, yeah. So anything all with 1, you get back the original waveform. So if you do this operation again and get this segment here translate to this one, and then like this segment over here, here, then you go down, then like this 2 segments over here, 1, 2 segments over here, and then this one, there's like extra. Okay, but so this waveform, you see that it is once again shifted. Okay, K0 is shifted. So shifted by 1 nanoseconds. Okay, so far following, right? Okay, so now what about the rest? So we can draw the same thing for K1. So we see that for K1, we have I1 and S. Okay, let me just change my screen. The color orange. Okay, so for K1, what is going to happen is we are now going to draw I1 and S. So we have this I1 over here and S. Okay, I1 again is 1 all the way long. Okay, all the way from the beginning until the end is 1. So the output of K1 actually would just depend on whatever the value that is as S over here. Okay, so S over here is like this, and the output at K1 will be the same, except the output will be shifted by 1 nanosecond. Okay, so the output here will be shifted by 1 nanosecond. So we don't have anything for the first 1 nanosecond. Okay, and then after that we just follow the waveform of S. Okay, that like that. Okay, so which is this 3 segment over here. This 3 segment over here corresponds to this, and then it goes down, and then it goes 2 segments low, down, it goes 2 segments low, and then like up again, like 3 for 3 segments. 2, 3. Okay. All right. So that is K1 with propagation delay. Okay. For the first 1 nanosecond, that's undefined. Now, finally, let's draw the output waveform. So the output waveform will just look at K0 and K1. Okay. So K0 and K1. And let's see if we have a glitch. K0, K1. Okay, it's just that. Now, for K0 and K1, we see that there are a period of time where there are no clear signals. The signals are not defined. Okay, so this time over here for the first 1 nanosecond, this K1 is undefined, and for an additional 0.5 nanosecond, K0 is undefined. Okay, so up to this point over here, we see that the output is undefined because there's no clear input signal. So the first time that there will be a clear signal is when we have this, and you want to OR it together. Okay, so 0, OR it 1, then you have 1 over here. Or is that the case? Now, you might be tempted to draw it over here, 1, but if you consider that there is propagation delay for 1 nanosecond, so you have 0 or 1, that result will only appear after 1 nanosecond. This is the propagation delay, and the result will only appear here. Okay, that is for this 2 segment. Okay, after that is 0 or 1, then the result is 1. 0 or 1, the result is 1. 0, 0. Let's just do half over here. 0, 0. Okay, then this goes down to 0, and then it goes up again over here. 1, 0, and then it's 1 over here. Then like it's 1, 0. Then it's 1. Then like it's 1, 1. Okay, it's 1, and then it's like once. Okay, so what are we seeing over here? So this is the hazard that we are talking about. Okay, so in this case, this is a static 1 hazard. Okay, static 1 hazard. Okay, so how do we know exactly if this is the hazard or like this is the real output? Okay, again, using the method that I showed you just now, you can always draw this one using the K-map, right? Okay, let's try this one more time so that it will be clearer to you. So we have I0, I1, and S. So we have I0, I1, and I0, I1, S. Let's say 0, 1. So you have 0, 0, 0, 1, 1, 1, 0. Okay, right. So let's take a look at what is the output expression over here. So the output is equals to let's see. So they have I0. So you have I0 over here. Then this is S bar plus with I1S, right? Okay, I0 S bar, okay, or with I1 S. Okay, let's map this on your K-map. So I0 I0 S bar. So let me change this in color again. So I0 S bar is 1, 0. Okay, I0 is 1, so I0 is 1. Let's just use I0. It's confusing. I0 is 1, and S bar is 0. So I0 is 1 is along this row. Okay, and S bar is here. Here is I1 and 0. And over here is 1 and 0 also. Okay, that is for the first term. For the second term over here is they're both 1s. I1s and S is 1. So I1 and S, so they are both 1s, okay, which means they are here. This is how the map looks like. Okay, so how do you get this expression over here is by grouping this and grouping this together. Okay, so from this group you would get I1S, just confirm it. From this group you would get I0 S bar. Okay, so the hazard happens when you have ones that is side by side or top and bottom, but they're not in the same group. So where is that? So I believe you can already see it. So it is in these two boxes. So these two ones here and here, they're side by side. Yes, they are adjacent to one another, but they're not in the same group. So that's why the hazard can happen over here. Okay, so let's take a look at this. In this box, what is the value of I0, I1, and IS and S, right? So the value is 1, 1, 1 over here. And the next box, the value is, this box, the value is 1, 1, 0. Okay, so the hazards happen when the value of S changes from 1 to 0 or 0 to 1. Okay, so which is what we are doing over here. So the value of S changes from over here is 1 and then to 0. This is where this hazard can happen, and then 0 to 1. Okay, so the value of S changes from 1 to 0. Okay, from 1 over here to 0 over here, or from 0 to 1. Okay, so in other words, when you transition between these two boxes, that is when hazards can happen. Okay, so then we know that, oh, okay, this is probably a hazard over here, a hazard. So how to mitigate this hazard is we need to put a redundant box, a redundant group inside there to make sure that there are no hazards. Right. So if you go and get the expression out over here, you'll find that this one is I0 and I1. Okay. So the expression, the final expression without hazard would be I0, I1 plus I0 S bar. Okay. So this is the final, the logic gate that you want to build without those glitches. Okay. So any question up to this point? Is it clear how to find glitches and how to fix them and how to visualize them on the timing diagram?
Okay, so far.
Okay. Okay, so if there's no problem, then let's take a look at one more. Oh, it's 1 hour already. Oh my God. It's almost 1 hour already. Okay, but we're at the end of our slides already here. So finding hazards, oh, this one I've covered just now. So these hazards can be found by adjacent 1 or 0, but they are not in the same group. Okay, I believe this one you guys are familiar already. Okay, now we're just going to do some very casual example to see whether or not you can find this hazards. Okay, suppose you're given a switching function f that has this mean term. Draw the logic implementation of the circuit with no hazards. Okay, so first step is we need to know where are the hazards happening, and then we can talk about how to fix them, right? So let's take a look at the minterms. So the minterms are 0 to 5. So I'm just going to write this down into KMap. 0, 1, 2. You have 0, 2, 5, 6. 0, 1, 2, 3, 4, 5, 6, 7. 7 is here. 4, 5, 6, 7. So you have 8, 9. 8, 9. 8, 9 is over here. 10, 11. 8, 9 is done. 10, 11, 12, 13, 15. So 8, 9, 10, 11, 12, 13, 14, and 15. So this is how they look like. Let's just double check. 2, 4, 6, 8, 10. So it's like 4, 8, 10. Okay, looks good to me. Okay, now let's take a look at how a hazard might happen. Okay, so as you might already be familiar with, a hazard can happen when there are ones that are side by side or adjacent to one another, but they don't belong in the same group. Okay, let's see how we can have that. Okay, so let's say you group this 4 together, then you group this 4 together, and then how do you want to group this? Group this 2 together, then you group this 2 together. So where is the hazard happening? Now, so the hazard can happen at this point. I'm going to highlight over here. The hazard can happen at, I'm not sure if you're seeing this, these two ones, they are adjacent, but they are not in the same group. Okay, so that's why over here you can have a hazard. So because of that, we want to have a redundant group covering these two ones. That is how we fix the hazard. Okay, clear? However, you can also see that there are other ways to group this as well. Okay, so if I erase all this, you can also group this in other ways, right? So just now we were grouping it like this. We were grouping it like this, right? So you can also group this like this here, and then like this here. You can group it like that also. Now, if you group it in this way, now where is the hazard going to happen? The hazard is going to happen within these two boxes because they're adjacent to one another, but they are not in a single group. So if you want to solve this hazard, what you want to do is to group them in a redundant group like so. Then you will not have any hazards going on. Okay, so I hope you're beginning to see over here that there are different ways you can group things, and there are different spots hazards can happen depending on how you group your ones in the K-map. Okay, so the simplest thing is to always spot this hazard by using K-map and try to group things. I think it's the easiest way to spot this if there's any hazard, right? And to solve them, you will just need to group put a redundant group inside of this. Okay, so this is an example question from your textbook, and I'll go through also some of this sample exam question. We are not going to solve them all, but we are going to. I'm going to walk you through how you solve them. All right. So I really do hope that this will be you do this as your assignment or your homework. Actually, I think in your next assignment this will be the question. All right. So this was some sample exam question from I think past few semesters. So this is what the questions will look like. So you're given some kind of switching function, w, x, y, z, and then you're given this min term. Okay, kind of similar like the first question. Now, first is find the simplest switching function in SOP term. So what does it mean? Simplest switching function means the simplified Boolean expression. So what do you do? So you already have here the min terms, right? So what you can do is use K-map. K-map, and that's how you get the simplest switching function. Okay. So alternatively, you can also use algebra if you want. Okay. If you like, but they should result in the same truth table. Okay. So that is how you get this question 1. Okay. I think it's quite straightforward. So implement the switching function using minimum basic logic gates. So what you can see over here is that minimum basic logic gate means you want the function to use as few logic gates as possible. So how do you do that? From your K-map, you should get the simplest switching function, right? F equals to some kind of a simple function, and then you want to implement this using basic logic gates. What does the basic logic gate means? These are NOT gate, these are AND gates, and these are OR gates. Okay, using only these 3 gates. Now, next question. Is there any hazard in this switching function? Okay, so in the last 2 examples, I've already covered how do you find if there is a hazard in a switching function. So it really depends on the K-map, on how you group it in the K-map. So if you have 2 ones that are side by side and they're not in the same group, then you would have a static 1 hazard. Okay, you can also have a static 0 hazard. If you have zeros, they're side by side, but they're not in the same group, then you have a static 0 hazard. All right. So if yes, identify the type of hazard. Okay. So most probably you have a hazard and it's going to be static 1, static 0. I leave it to you to find out. And then after that, you should draw a waveform. And waveform is exactly like what we did just now in that example, drawing the waveform on a graph paper. Okay, in this case, like we don't have graph paper, you can draw it on your graph paper, or you can even draw it on a computer, and you have this. Assume that all gates has got this propagation delay. Okay. In the previous example, I've just picked a random value of 1 nanoseconds, but this value, it's not important because this value changes from one manufacturer to the other manufacturer. Okay, so in this example, we assume that all gates have a tau seconds of propagation delay. So this tau seconds can be 1 nanosecond, 2 nanosecond, okay, or whatever. Okay, this is just a variable. And then draw that, and finally you are supposed to fix this hazard by using the method that I showed you just now, drawing a redundant group and then redraw the circuit again. Okay, so there you go. This is like a one question in the final exam, like one question. So that's like worth 20 marks over there. Okay, so I believe at this point you are supposed to be able to solve this with ease. Actually, it's very easy already, given what we've covered in today's class. Okay, so this is also another final exam question. So this one is not related to hazard, but I really do hope you would go through this question because you would see this question again in your project. So do ponder about how to solve this question. All right. So that is all for our class today. Wow, we are right on time. We are 4:01 today. Any question before we end our class today? Okay, if there is no question, then that will be the end of our class today. And that will be the end of topic 5. So going forward, we'll be covering topic 6 and above. And I understand that today is the last day of, no, it's not last day, is the last class we covered topic 5. So after this, I'll release to you assignment 5. So you have 1 week to submit your assignment. And I understand also next week is your midterm break, right? And it's also the time when we will be doing our midterm project. So I'll talk about midterm project in our Thursday's class. I'll give you a briefing on what it is all about, and then you would have like maybe 2 to 3 weeks to complete your midterm project. Okay, so that is all for today's class. If any questions, please feel free to stay back. I will try my best to answer all of your questions. If none, then I'll see you again on Thursday morning class. Bye-bye. Take care, everybody.
Thank you, sir.
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 All right, you're welcome.